Today we are going to discuss in this video some commonly used reference frame that we find its heavy application in our electrical machine transformation. In my last video I discussed about last two videos I discussed about torque and torque matrices, and prior to that we discussed about something different uh, impedance matrix for different structures. Sometimes we consider salient poles, sometimes we consider induction machine. Here today we are going to discuss some commonly and this is going to be a very important topic for you because you need to apply this concept to understand the things, and means in your final year project you may find application of Clarke and Clarke transformation even if you are doing it in like in pure power electronics, but still quite often you will find that this application or usefulness of these transformations or this rotating reference frame, they are not only limited to our case of electrical machine, but they are also means find a heavy application in power electronic sector. Even in some case, if you deal with inverter problem, you may find its application. So let us start with this, right? What are the reference frame that we may find very important? See, we can have few different types of reference frame we can have. One is arbitrary reference frame. What is this arbitrary reference frame? In arbitrary reference frame, what happened yes, this arbitrary reference frame, what happens that the speed is we can have the reference frame speed, and reference frame can rotate at a arbitrary speed. It is not like specified to some particular value. Another frame what we can have is that the frame that is attached to our stator. So stator attached or stator fixed reference frame. Another frame is rotor attached reference frame, and the last one is synchronously rotating reference frame. Now here we would like to have a further clarification. Say, let me write it very clearly that reference frame speed, that interpretation of such speed variables and corresponding transformation. So first let us consider the case of omega unspecified, that is arbitrary case. So what you will get here, this indicate what? This indicate stationary circuit variables refer to arbitrary reference frame. Say, what we can do is that we can consider the the reference frame is rotating at a slip speed. Well, this slip speed, or it can have any arbitrary speed. For an example, I am considering the case of slip speed. But why this is arbitrary? Because see, what is the difference between rotor speed and slip speed? Uh, Suppose your machine is rotating at synchronous speed is 15,000 rpm and machine is rotating at 1400 rpm. Now the slip speed is 100 rpm. So if I am specifying any machine that is rotating at 100 rpm, the reference frame is rotating at 100 rpm. That means the reference frame is rotating at slip frequency. But it is not means always means arbitrary, means it can be anything. It can be 100, it can be 1500, it can be even 3000 also. It can be anything that is completely unspecified and will be chosen based on our requirement. The variables will be obviously generally, if in terms of our impedances, it will be like this is sorry. Now, if the reference frame speed is 0, then what does it indicate? 0 indicate it is you are having this is the common case which we are quite accustomed with in our normal AC analysis. What we do, that is just this one. How we indicate this variable set. Do note that I am trying to maintain a parity between the two, like what we were having there for that Tron's representation and this. But you must also be a bit mindful what is required in a single problem. You use a simple and uniform notation. Do not mix up the notation, otherwise we may get confused. It is just as simple as, like, sometimes if you use psi as your flux linkage, and in the next instant if you use phi as your flux linkage, then that will means confuse everyone. And an obvious inference will be that the student doesn't understand the difference between flux linkage and flux. But it may be the case that you know the difference, you know that flux linkage is equal to number of turns into flux, but due to your carelessness or due to you do not didn't pay proper attention while writing it, you made it uh, problematic for the examiner to judge. If you write psi and phi sometimes interchangeably without maintaining any uniformity, people will get lost. So what is the plan here is that to stick to a particular type of notation. This gives us what? Now we can have what? We can have omega r. What is that? Stationary circuit elements refer to our rotor. Better we write variables. So what you will get? So that gives now the last one is that is stationary circuit variables refer to the synchronously rotating reference frame. That gives you this, right? Now this in case of AC machine, this omega is the electrical angular velocity of the air gap rotating magnetic field that is established by our stator current. Generally the stator carries the supply current or connected with the main supply side. Now these notations we need to understand their in-depth uh, means underlying concept there. Uh, these circuits which are stationary in real life as opposed to rotor circuit like which are free to rotate. Now this raised index ds this index denote this r or here this e, they denote that qs and ds of the arbitrary reference frame which carries that no raised index. And obviously for zero variable, although I have written this, but what we can do is that we can drop it, because if you can recall that zero variable is actually the transformation invariant variable. It doesn't change. If you change your system variable, it doesn't change. So, yeah, this transformation of stationary circuit means to a stationary reference frame was developed by our his name was E.S. Clarke, and he coined the famous Clarke transformation. What was that famous Clarke transformation? In that Clarke transformation, it was your, but his case it. So let us consider first the Clarke transformation and what it did. In that Clarke transformation, it is named after Mr. Edith Clarke. His name was right. So what that gentleman did, he proposed something to convert your three-phase ABC reference frame alpha, beta, gamma reference frame. So, what the primary value of the Clarke transformation is doing? It is considering that reference vector which is common to all three-phase components. Basically, it is trying to convert everything in terms of your like that two-phase to means three-phase to your means you can say it converts it to time invariant oscillating signal, means a signal that is like, sorry, not time invariant, rather space invariant, but oscillating in time. So what he did, Clarke, he proposed a transformation matrix like oh, root 3 by 2 1 by root 2 1 by root 2. So this converts this ABC referred column vector to the XYZ reference frame, and the vector must be so pre-multiplied to give us the uh, this is done keeping our power invariance in means consideration. Now, if you want to convert it back, we can easily prove that this matrix is an invertible one, and we can have our KC inverse exist for us, and from that, if this matrix like from ABC, if we get, say, this is we can write V alpha beta naught is equal to KC V your ABC. This gives, then we can have V So basically what this Clarke transformation is doing, your MMF or means whatever electrical signal with respect to a fixed reference means it is you can say it's rotating in space. But what this Clarke transformation is doing, it just makes it like one part that is oscillating, another part that is also oscillating, but those parts that are oscillating with respect to time, they are not moving with respect to space. They are maintaining, or not remain, they are maintaining the same space position as it was, right? Because if you perform this equation, what you will get, I am talking about this first equation, what you are going to get for even if you consider a balanced one, you will get something that is not not moving, it's oscillatory in nature. So that is very important understanding here. Now, if we consider the other two part, they are also somewhat nature that it cannot be like there cannot be any oscillation, means now what Clarke did once he considered this Clarke transformation. So if you are still having doubt, let me show you that how these things are working in reality. If we consider something like, say, our, well, right? Now if we apply our this matrix on this particular one, then what would we get? We will get a very interesting things, that it will give us something like your here I have considered that I is the RMS value of all these winding, and it's I'm obviously considering a balanced case. In that one, if we apply this matrix over this one, what you will get? You will get I alpha will be something like root 2I cosine theta t. I beta will be root 2I sine theta t, and I gamma should give you 0. So this gives a very clear indication that what I wrote here in this form is that just a minute. Yeah, so this gives you a very clear indication that I'm a bit confused with this root 2 or only 2. Sometimes it is only 2 by 3. Okay, whatever, you just check it. You should get these values. And what is the physical interpretation of this one? This is a power invariant transformation. Once you do it, what you will get, that the in terms of your this alpha beta gamma, what we can write, I alpha will be how much? Well, yeah. No, I was right. It should be. Why that it is not moving? I do not know what's wrong with this. Yeah. So basically, this becomes that here I need a correction. Root 3 so one thing that is quite obvious in this like in this discussion, that here it is like, as I said, it represents things in a stationary frame. This alpha, beta, all of them are stationary in space but oscillating in nature. Now, if we want a kind of DC representation from this, well, before going to Clarke, let us have the geometric interpretation also. The geometric interpretation, we can consider that it represents the three-phase quantities onto our two stationary axes, the alpha axis and beta axis. But we just convert this three-phase to kind of two-phase without any loss of generality. We can consider this I gamma responsible for our zero sequence component and for all balance analysis. Rather, even if it is unbalanced but symmetrical, all the time we will get I gamma is equal to 0. But this I gamma, we can visualize it as it is something that is perpendicular to the plane, and therefore it is orthogonal, and the transformation matrix is always invertible. Now this this is what the geometry indicates. Now from this we can go to our DQ0 transformation, or what is given by Clarke. So what Clarke did an interesting things from the Clarke transformation. He proposed something to convert your these stationary alternating quantities to be space varying, time invariant direct quantity. Let me repeat: space varying, time invariant direct quantity. Again, if you are getting confused, let me tell you, it is like if you are standing on a platform and if a train is moving, then the train appears to or means your eyes will perceive the exact speed of the train at which the train is moving. If the train is moving at a speed of 20 km per hour, your eyes will measure the speed 20 km per hour. If you stand or if you are standing on a platform, that is, the platform is the stationary reference frame. And if suppose, although that is very weird and difficult to visualize, but if the train executes a kind of to and fro motion, standing on the stationary platform, you will also see that the train is going to and fro. However, if you have something like a train, means that is also moving on a parallel rail on which the train under observation is moving, then from that another cart or another rail that is moving on a parallel rail to this first one, to this first train, what you will see, it all depends on your speed. And if by some means you are able to interlock it, how? Just if you can make sure that both are moving in the same speed, and if you get a chance to board on the second train that is moving on a parallel rail, you will find that, or your eyes will give you an indication that this first train, which you are means able to understand that it is moving at a speed of 20 km per hour when you are standing on the platform, but when you are sitting on inside a rail that is moving at a speed of 20 km per hour through a parallel rail or on a parallel rail, exactly means at the same speed of that your train, now your train will appear to you as a stationary. That is what Clarke approach. Let us make the transform the reference frame rotate and let us exploit it to realize our direct current. Now, if you get surprised at what is the motto behind this kind of weird understanding, then let me tell you, it was his means observation that, if you recall, when we discuss a very primitive discussion, preliminary discussion on transformer transient, at that time a significant amount of transient comes in picture when we consider the AC. When we are talking about switching the AC, at which instance we are switching, that used to play an important role. But for a DC, as it is steady, at any time point you can switch and you will always get a similar kind of response. So the essence of converting it to a rotating frame where the variables will appear as a direct current variable is that you will be able to analyze and understand this transient without having much difficulties, right? So what Robert Clarke did, that he just converted or bring another matrix that is known as path transformation matrix. Where theta is the instantaneous angle of an arbitrary frequency omega, where omega is your rotor speed. Here what you can see is that it's very interesting. If you apply this transformation on that previous one, on this combined effect, this will give you things like, how to make you understand, so 0 minus root 3 by 2, sorry, So this gives sin theta plus 2 pi by 3 2 by 3 root 2 by 3 and root 2 by 3, right? Now if you do this, you will see that it magically simplifies all the things and gives you a system in direct current. Right now I am not going to discuss more on this Clarke transformation, or rather I would like to conclude this video here. In our next video we will see what more we can do with this transformation. Right.